to start talking about radicals and rational exponents. Okay, so what's a radical? Well, the radical sign looks like this. Okay, inside you have what's called a radicand. Over here is what will be called the index, and the whole thing together is called a radical expression. Now, you can simplify radical expressions like that. Simplified. In this case, we just found the square root. Let's evaluate a few more square roots. I can say radical 64, but to be more specific, what kind of radical is it? It's the square root of 64. Of course, we know the answer is 8. If I have a negative in front of the radical sign, and it's a square root, that means that this answer is going to turn out negative. I'm going to do the square root first, and then apply the negative sign. If I do a square root of a fraction, well, I ask myself what number times itself equals 1/4. And the answer is going to be 1/2. I pinned myself. Now you actually have to pin me on your screen if you want to see it better. So when I say I pinned myself, it's for video purposes, and my entire screen is just showing my work and not your faces. So, and if you want to, I recommend not typing in the chat right now if you want to tell me something. Go ahead and just speak up. Nobody will know it's you, don't worry. Now, let me give you two very confusing types. Yes, I'm recording this video for everyone else. You know what's weird? Let me tell you something. Did you notice in my video, all of my tabs and everything were in reverse? This thing records a mirror image, and it takes me forever. I've got to process it and turn it back the right way for everyone to see. I'm still trying to solve this problem, so let's see what happens with it. Okay, let's take a look at two problems real fast. 9 plus 16 and 9 plus 16. Those are two different types of problems. In this one, we have to add the 9 and 16 inside, giving us 5. Here, you have to simplify each one individually and then do the addition. Okay, I hope you see the difference. Does anyone have a question right now?
I can't see the left side of the paper. Thank you.
Welcome. Okay, I'll leave that there for 1 second. Okay. Let's see what happens when we throw some variables in the mix. What do you think is the answer to this?
Itself.
Itself meaning A? You think it's equal to A, correct?
Yes.
Let's do this. Let's let A equal -2. And let's see what happens. So radical -2 squared, well, it seems like it should be radical 4. And we know radical 4 equals 2. See, I squared the inside first. But wait a second, this is not the same as A. Something's wrong. So here's the problem. When I see the radical sign by itself, this is called the principal root. This is positive, or 0. If I see a negative in front of the square root sign, this is going to be a negative number. How do I make sure this turns out to be positive? Well, Because look here, a was negative, but then the answer is positive. So here's what we write. Square root of a squared equals a if a is greater than or equal to 0, if it's positive, and it equals negative a, or the opposite of a, if a is less than 0. And to summarize it, you could just say absolute value of a. That makes sure that it turns out to be the positive answer. Crazy, huh? Not what you expected. So let's see how this works. What if I had the square root of x to the 4th? Well, I'm going to really focus on using this bottom one here. And I know if I'm doing the square root of a variable expression, I get the square root and in absolute values. But you know what? X squared is already positive, whether you're positive or negative. If I square -5, if I square 6, it already turns out positive. So I can take off the absolute values. But let's say I do the square root of something to the 6th power. I get the absolute value of x cubed, and I can't go any further because I cannot guarantee this will be positive. If x were a negative number, this would turn out to be negative, so I have to leave it like this. If it reduces to an even power, I can take off the absolute values. If it reduces to an odd power, I have to leave it on. Okay? In general, when you do the problems in the homework, it's going to say, assume x is a positive number. Well, if we assume x is a positive number, then we don't need the absolute values. But I have to show you because it's knowledge you need to know. Any questions? Because I will remove this page. When I reach the end of a page, you may want to screenshot it so you can finish your notes from it. Or you can watch it later on YouTube and you can pause whenever you'd like. Okay, continuing on. We've got our product and quotient rules. And let me write out the product rule. Okay, radical AB is equal to radical A times radical B. We say this. We say the root of a product is the product of the roots. The root of a product is the product of the roots. Okay, neato. Let's see. I'm going to go in reverse. I'm going to say radical 3 times radical 27. Okay. Well, this is the product of two roots that are the same kind of roots. They're both square roots. So I can say that's radical 81 because 3 times 27 is 81. Oh, look. I simplify it down to 9. Well, that's cool. Cool. Likewise, we have stuff like square root of 24. And, well, that's some long decimal, right? But we can simplify it. And here's how we'll simplify it. We're going to find the biggest perfect square that goes into 24. Your perfect squares are 1, 4, 9, what's next? 16, 25. So you go 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Those are your perfect squares. So what's the biggest perfect square that goes into 24? Well, the answer is 4. So I can rewrite this as 4 times 6. I can now separate them, and I can actually take the square root of 4. And I get 2 radical 6. Square root of 24 equals 2 radical 6. Why don't you guys try one of those? Tell me what the square root of 40 is. Go ahead and do it. I'll give you about a minute. When someone gets it, you can tell me the answer. Here's your perfect squares. What's the biggest perfect square that goes into 40? Well, that's right. It's 4. 4 times 10. We can split it up as radical 4, radical 10, and that gives us 2 radical 10. Sometimes you're going to have big numbers. Let's say, for example, radical 500. And we know that 100 goes into it, but let's act like we don't know that. Our mind's blank today. And I say to myself, you know what? I know 25 goes into it. And I think, how many quarters are in $5? 4, 20 of them. Okay. So I'm going to simplify it with 25 and 20, giving me 5 radical 20. But now you look at 20 and say, okay, I can reduce that further. So I'm going to get 4 times 5. Sorry, rewrite. That first one shouldn't have been under radical. 5 times 4 times 5. See, it's a big deal which numbers have come outside to play and which ones are still in the house. See, 25 is perfect, so it got to come outside and play. Became a 5. 4 looks perfect, so 4 is going to come out, become a 2. All the people who are outside get to play together, multiply it and get 10, and 5's a bad boy, stays in the house. There's your answer. And you can see where that 100, if we'd taken out 100, it would have become 10. Okay? With attendance taken, attendance will be dealt with once I give you guys work and once I'm done with the lecture. Anybody need to do this right here? Take a screenshot. Moving on. So the quotient rule is almost the same thing. So if I have square root of 8 over square root of 2, a lot of people want to, kind of fix the square root of 8 up and take out a 4. Don't do that. If I can reduce this, think if that might be a good move first. And 8 divided by 2 is going to be 4. Okay, I'm done. My answer is 2. What if you did it the other way, where you simplify the top? Well, square root of 8 is 4 times 2, which is 2 radical 2. I can put this in place of radical 8 on top. And my radical 2's cancel. So I got the same answer 2 different ways. Okay. Let's take a trip back in time. How do you combine like terms? Well, since you already know how to do it, let's talk very specifically why it works, and let's use the right vocabulary. Since these are like terms because they have the same variables and the same powers of those variables, I can add the coefficients. Why can I add the coefficients? Because my IM 1, 2, or 3 teacher said I could? The answer is no. There's mathematical reasons for everything. We're going to apply the distributive property in reverse. Instead of distributing something to 3x and 4x, we're going to undistribute an x. That's called factoring. When you factor out an x, you're left with a 3 here and a 4 there. We can now combine the inside by addition, and you see how you combine like terms. So combining like terms is the distributive property in reverse. Okay? So just for fun, can we combine these terms? 2x and radical 3x? Well, the answer is yes. Take out an x, and this is your coefficient. This is ugly for some, I know, but if you think of it this way, it's just a number. It represents 1 point on the number line, and that's how many x's we want. And what is this approximate number? It's about 3.7. You can do it on your calculator. It's about equal to 3.7x, and so forth. Now, why are we doing this? Well, because combining radicals is basically the same thing. If I've got 4 radical 2's and 8 radical 2's, well, then I have radical 2's in common, and I add the coefficients. Gives me 12 radical 2. Well, sometimes the problems are going to require some simplifying first. For example, 3 radical 2 plus 5 radical 8. I don't see anything in common, but I do recognize that 4 goes into 8. Let me simplify this and see if that helps. 5 radical 4 radical 2. Notice 4 times 2 equals the number underneath the radical. 5 times 2 radical 2. I took the square root of 4. And finally, 5 times 2 is 10. I can multiply numbers that are outside together or numbers that are inside together. Oh, take a look. Now they're both the same type of term. I can combine the coefficients, and I get 13 radical 2. This right here is 13 radical 2. Okay? Subtracting radicals is the same process. Now, if you have several terms here, you've got to figure out which ones, after simplifying, which ones go together and which ones don't. Next up, we've got something called rationalizing denominators. In general, we say that we cannot leave a radical in the denominator. So let's do a very simple one. This has a radical in the denominator, therefore it's not simplified. How do we get rid of the radical? Well, we multiply top and bottom by something that will make the radical disappear, normally by itself. Radical 2 times radical 2 on the bottom is 2, because it's radical 4. Radical 4 equals 2. And the top is radical 2 over 2. Sorry, 1 times radical 2 is that. It's very strange that this number and this number are equal to each other. You can verify that on the calculator. Okay. So one more example of those types. How about 8 over radical, let's do radical 6. So let's multiply the top and bottom by radical. Let me introduce a, hang on. Let's do it a little better. Let's do 8 radical 5. Okay. Multiply top and bottom by radical 6.
Do you think you can go back up a little bit? Thank
Just so you know, if you are struggling with keeping up with the notes while I do them, you might want to kind of just use your paper for trying out problems. And you can check out the video later to fill in the notes. You can leave a little space for each part that where I might have gone just a teensy-weensy bit too fast. You want to really focus on the math I'm doing more than keeping up with writing. Check out the top and bottoms here. The top becomes 8 radical 30 because 5 times 6 is 30. The bottom becomes radical 36, which is 6. Now you see the way I have the 8 and 6 that are not in a radical? I can reduce them. 2 goes into 8 4 times. 2 goes into 6 3 times. I get 4 radical 30 over 3. Can I reduce the 30 and the 3? The answer is no. 30 is under a radical, 3 is not. Therefore, you cannot interact with them, if you will. It's kind of like I said earlier with the being in a house and being outside. If your friend is inside their house and you're outside, can you guys play football together? The answer is no. So 3 and 30 cannot cancel because 30 is inside the house, 3 is outside of the house. 4 is outside of the house too. So since 4 and 3 are outside of the house, I could write my answer like this. These are the same answer. When you have a number without a number underneath it, it goes with the numerator. Okay, so that leads us to a very, how should I say, radical problem. What do we multiply top and bottom by to rationalize this denominator? We can't leave the radical in the bottom. So how do we rationalize this denominator? I'll wait for any of you to tell me. Go ahead and unmute your mic and tell me what you think we should multiply top and bottom by.
Rad 2.
Radical 2. I mean, it just seems logical, right? Let's do it. So 1 times radical 2 is radical 2. And on the bottom, I have to distribute. You agree with that? I hope you agree with that. So radical 2 times radical 2 is 2. And 1 times radical 2 is, whoa. We didn't eliminate the radical here. We just kind of moved it. We got rid of the first radical, but now we made a radical on the right-hand side. Something didn't work. So let's cross this out, and I'm going to show you how you use something called conjugates to rationalize the denominator. When you have more than one radical on the bottom or two terms where one of them is radical, here's what we do. I think it's going to blow some people's minds. We have to multiply the top and bottom by the conjugate of the denominator. And when I say the conjugate, all you do is you change the middle sign. I'm going to make it radical 2 minus 1. Okay? Now, quick sidebar before I continue. Do you remember how to do a plus b times a minus b? That's the difference of two squares. When you FOIL it or expand it or distribute it, you're going to come up with a squared minus b squared. Well, the same principle is going to help us out here because our denominator is now going to be radical 2 squared minus 1 squared. And what's radical 2 squared? Well, that's 2. What's 1 squared? That's 1. Our denominator is 1. These two denominators multiplied together equals 1. And you can go and verify it on your own if you need to. Now the top is easy. 1 times radical 2 minus 1, you can think of this as a whole. And I get radical 2 minus 1. Final answer is radical 2 minus 1. This original fraction here equals radical 2 minus 1. I almost recommend that when we do our homework later, you go straight to these problems because this kind of includes everything we've done. And make sure you can do these ones. Okay. What if we have a different index? Do you guys want me to, do you need me to do one more of these, by the way? Speak up if you want me to do one more or if you're okay with us going on.
Yes, please do one more.
Okay. Let's do 4 over radical 3 plus 8. Okay. I have two terms on the bottom. One of them is a square root. Therefore, I will multiply top and bottom by the conjugate. The conjugate means change the sign of the middle of the two terms. Okay. Our bottom is going to become a squared minus b squared. So a squared minus b squared. The top we have to distribute. 4 radical 3 minus 32. Now let's simplify the bottom. This is 3. This is 64. 3 minus 64 is negative 61. I don't see any way that we can simplify it further. This is your answer. Tell me if you have any questions on here. Did I do a step that you need to verify? Let me know right now. Going once. Going twice.
How'd you get negative 32?
4 times negative 8.
Okay.
We distribute. Okay. Just so you know, when we have a negative down here, I could multiply top and bottom by negative 1. And that would change our answer to 32 minus 4 radical 3 over 61. Multiplying every single term by negative 1 changes the direction of this to 32 minus 4 radical 3, and the bottom becomes 61.
Quick question. Would you like the answer like that in the homework or?
I'm not going to be picky. The reason I'm telling you this move right here is because if I give you a multiple choice test, either one of these could be on the multiple choice, and so you need to know how to go back and forth between these. That's all. A final possible answer could be this as well. Negative with the fraction bar, like equal to the fraction bar. 4 radical 3 minus 32 over 61. These are all three the same answer. It's kind of crazy, but that's how it is. That's how it is. It's like there's 10 different ways from my house to Chino High School. It is what it is. Any questions? Taking it away, and here we go. Sometimes you don't have square roots. Sometimes you have other roots, like perhaps fourth roots. Let's do a fourth root of, I don't know, let's see. I'm trying to make up a problem now. This is what I shouldn't do, but I will. Fourth root of 96. Okay.
I can't see it.
There we go.
Thank
Yeah, thank you. Fourth root of 96. So I do factor trees. I also do factor trees for the square roots. I just didn't teach it that way today. I did it with the greatest perfect square. Here's how you do this using factor trees. The first prime factor that goes into 96 is 2, and you divide it out. Everyone agrees that 2 times 48 is 96. And then I ask myself, can I take out another 2? The answer is yes. And then I say, can I take out another 2? The answer is yes. And then I say, can I take out another 2? The answer is yes. Another 2. And voila, we have all prime factors on the bottom. Now, for a fourth root, I want to circle groups of 4. There's 4 2's, and these I call leftovers. What I'm really going to do now is rewrite my fourth root of 96 using the product rule. These 4 2's go together. 4 2's is 16, by the way, when you multiply it out. I'm going to write as 2 to the 4th. And over here, my leftovers, I'm going to multiply them together, 6. Now let's separate this. I get the fourth root of 2 to the 4th times the fourth root of 6. Fourth root of 2 to the 4 is just 2. 2 gets to come out and play because there's 4 of them. Leftovers stay home. They have to stay in the house. And that's how you reduce a fourth root. Any questions? Do you need to see another one?
Did you cross cancel the 4's to
Here?
get the 2? Yeah.
Well, the thing is, when you do a fourth root, it means what times itself 4 times equals the number inside. So remember when we did like square roots? So let's say square root of 25. What we're really doing is what number times itself twice, because it's a square root, is going to equal 25. See, so you could say, yes, the 2 and the 2 cancel out, giving you 5. And actually, in about 5 minutes, when we go to rational exponents, you will see exactly how it cancels out. Maybe I should do one more. Let's do the third root of 27, how about 270 x to the 4th? Okay. So let's start doing the factor tree. 2 goes into it how many times? My calculator says 135. Does 2 go into it again? The answer is no. Let's try 3. 3 goes into it 45 times. Does 3 go into it again? Yes, 15 times. Does 3 go into it again? Yes, 5 times. Look at how we have our prime factorization. These are all prime numbers, and this is like the DNA code for 270. There is no other number that has 1 2, 3 3's, and 1 5 and nothing else. Now you see the x to the 4th? I'm just going to write out 4 x's here, because that's kind of like the rest of the factorization. We're doing cube roots. Let's circle groups of 3. I have 3 3's, and I have 3 x's. When I rewrite this, I'm going to rewrite this as 3 3's, 3 x's, and leftovers. But what are my leftovers? I have a 2, a 5, and an x. When I multiply those, I get 10x. Cube root of 3 means 3 comes out. Cube root of x cubed means x comes out. And my leftovers are 10x. Since this is an odd index, I don't have to worry about absolute values. If it were even, I may have to worry about absolute values. Be sure to circle your answer so I can find it. Any questions? Going once? Twice? Moving on. I'm removing this page. We're almost there. We're almost there. Okay. So now we've got rational exponents, and rational numbers, as you figured out, means fractions. What does it mean when you have a to the power of 1 over n? Well, the n in the denominator here means the nth root. So let's do some examples. What's 25 to the 1/2? Well, that means square root of 25, which is 5. How about the opposite of 81 to the 1/4? When you have this rational exponent, it applies to the number here, but not the sign. The sign goes outside of the radical sign. I can do the factor tree and the whole thing that I did a moment ago, and I'll see that this equals -3. How about if we have inside of the parentheses like this? Well, then that means it goes inside the radical sign. Okay. Now I can use the product rule here and take the negative sign right outside, because the cube root of -1 is just -1. Cube root of 8 will be 2. Not also, but 2, the number 2. And what about with negative rational exponents? Well, that just means do a fraction. And that means 1 over cube root of 27. And the cube root of 27 is just 3. Any questions? Going once, twice. Examples like these are in your book as well, and in the PDF that I've attached. Let's kind of see if this really works the way it says it does. Let's do 5 to the 1/2 power. A moment ago, we just said 5 to the 1/2 is the same thing as square root of 5. Now let me ask you, if I were to multiply square root of 5 times square root of 5, what do we get? I'll wait for an answer. Someone shout it out.
Square root of 10.
Let's try again. The product rule says that we multiply what's underneath. That gives us square root of 25, which is what? Try again. What do you get?
5.
5. So if these are the same, then I should be able to multiply it by itself and get 5. Let's see. So the product rule from exponents, which we learned yesterday, says add the exponents, right? And that equals 5 to the first, which is 5. You can see it works identically. Here's with rational exponents, here's with roots. We get 5 both ways using the different properties and rules. So what happens now if we have a numerator? What happens if we have a numerator? Well, let's use our exponent rules from yesterday and separate the numerator into 2 parts. I mean, the fraction into 2 parts. Would you agree that this is 25 to the 1/2 times 3? 1/2 times 3 is the same as 3/2. And now if I have a product here, I can put the lower one into parentheses and raise that to the third power. This already shows us what the numerator does. The bottom is the root and the top is the power. When I see the root here, I'm going to get radical 25. Whatever my answer is, I'm going to raise that to the third power. Gives me 5 to the third, or 125. Now what's really crazy is, you see these two numbers here? I could have done it in reverse. I could have done 25 to the third and then take the square root. I don't know what 25 to the third is. You tell me what it is. What's 25 to the third? Anyone? You have your calculators with you? Your phone?
25 to the third, right?
Yes.
It's 15,625.
15,625. And now if you hit the square root, what do you get?
Um, $125.
There we go. So you see we got the same answer both ways. So now let me write it out algebraically. Take a screenshot if you'd like. I'll pause for 3 seconds here. Okay, once again, this will all be available later on the YouTube video. And so here's what it comes down to. X to the m over n equals the nth root of x to the m power, or the nth root of x to the m power. Okay. Sometimes we're going to see expressions that can be reduced. For example, the third root of n to the sixth. When I write this as a rational exponent, the root goes on the bottom, the power goes on top, and oh look, 6/3 is equal to 2. There it is. You'll have a couple of problems based on that. That is our complete lesson. Does anyone have any questions? Okay, I will stop the recording now.